Hi, welcome to this lesson on Euclidean geometry, the Pythagorean theorem. Let's have a look at question 6. We're given two circles here, a large blue one and a small red one with the given information. The line TSR is the diameter of the largest circle with the center S. Chord TQ cuts the smallest circle at the point M. PQ is a common tangent to both circles at the point Q, and we're given that SQ is drawn with RP being perpendicular to PQ and MS being parallel to QR. Okay, so quite a lot of information. We want to prove that SQ is the diameter of the smallest circle. So this line here, we want to show is the diameter. So to show that that line is a diameter, there's one or two things we could do. We could show that if we know the center of the smallest circle lies on this line, then it's definitely a diameter. Or we can show that since the line SQ subtends to angle M2 here in the smallest circle, if we can show that that's 90 degrees, then that angles in a semicircle would also prove that that's the diameter. Since we don't know that the center lies on this diameter, on this line SQ, we can't really prove it that way. So let's try and prove that angle M2 is 90 degrees, and then we can use angles in a semicircle. So let's try to work backwards. How can we show that angle M2 is 90? Well, if I can show angle M1 is 90, then angles on a straight line would give me M2 is 90. But notice angle M1 lies on this F shape here, right? And these two lines here are parallel. So I could use corresponding angles. So if I could show this angle is 90 degrees, then I'm done. But if we look at this angle here, Q, that angle is being subtended by a diameter line in the largest circle. Okay, so we're actually done and we can work backwards now. So here comes the proof. So I can say that angle TQR equals 90 degrees. And again, that's angles in semicircle for the largest circle. All right, then I can say angle M1 equals angle TQR. And again, that's because MS is parallel to QR. And that is because corresponding angles are equal. And therefore, angle M2 must also be 90 degrees, which is M1. And that is because angles on a straight line, they must sum to 180 degrees. Okay, so therefore, since angle M2 is 90 degrees, we have that SQ is a diameter of the smaller circle. And again, the reasoning is angles in semicircle for the smaller circle. All right. Next, we want to prove this equality. So again, in Euclidean geometry, when you want to prove an equality, there's usually some sort of simplified proportion we can create. And then from that proportion, we can work backwards to see what two triangles we need to isolate to show that they are similar to each other. Okay, so first of all, this is true if and only if I divide both sides by RQ, then I'm going to get RT over RQ equals RQ over RP. So I'm looking for a triangle that has R, T, and Q, and I'm looking for a triangle that has R, Q, and P. So let's look in this diagram. R, T, and Q is this larger triangle. Okay, so here's the point T, here's the point Q, here's the point R, and that's angle R1. And then in the other triangle, we're looking at the smaller one here, QPR. This is angle R2, and that's a 90 degree. So since they have a 90 degree angle, that's really helpful to us. So I can say that angle TQR is 90 degrees. Okay, and that was from angles in semicircle. All right, and then I can also say that angle RPQ is 90 degrees, and that was given because RP is perpendicular to PQ. Okay, so therefore we have angle TQR equals angle RPQ. Okay, so we've shown that those two angles are equal. All right, so we need to try and figure out which two triangles, or not figure out which two triangles, but the order in which we write the two triangles. So since Q is the 90 degree here and P is 90 degree here, that's going to be the middle letter. So we need to figure out which other two sides or which other angles are going to be equal to each other. So I want to notice angle Q3 here. That angle lies between a tangent line QP and a chord QR. And if I use the tan chord theorem, that subtends to the point T. So I can say that angle Q3 equals angle T, and that's from the tan chord theorem. All right, so angle Q3 in this triangle, in angle RQP, must be equal to the angle T here in this triangle TQR. So if I put T first, okay, then that means angle Q here must be first. So the last sides here are R and R. So this is what I want to show. If I can show that, then I can use this relationship to prove this proportionality. All right, and then lastly, because we've shown now that angle Q3 is equal to angle T, this means that angle R1 equals angle R2 by angles in a triangle. Okay, so this angle R1 here must be equal to this angle R2 by angles in a triangle. So therefore, we've shown that triangle TQR in that order is similar to triangle QPR. Okay, so this is the many ways you can work backwards, reverse engineer what triangles you're actually trying to show are similar. Okay, because there's a very specific order we need to show that they are similar in to get these proportions. Okay, so I see an RT, which is over here, and I see an RQ, which is over here. So if I take that exact same sequence, I must be looking at QR and PR here. So therefore, so let me just write the reasoning here, angle, angle, angle. So if I look at RT divided by RQ, in that same sequence, we must have RQ divided by RP. All right, and that's exactly what we want to prove, because we cross multiply, you get back this expression here. All right, that equation. Awesome. Okay, so that's how we would do this one. And then lastly, we're given that the side length MS here is 14 centimeters and PQ is the root of 640 centimeters. We want to calculate with reasons the length of the radius of the larger circle. So I'm going to go into this larger circle and identify all the lines in the circle that is actually the radius. So S is the center. So this must be a radius line, TS. SR must be a radius line, and SQ must be a radius line. So I notice something immediately off the bat, that triangle TSQ is isosceles because you have two radius equal lengths here. I also note that this side here, MS, is equal to itself. It's a common side. And I know that these are right angles. I've proven that earlier. So my claim here, first of all, is that triangle TSM is congruent to triangle QSM. All right, and my reasoning is going to be right angle, hypotenuse, common side. Okay, so where does that come from? Well, the right angle, M1 equals M2 equals 90 degrees. We've proven that earlier. Right, angle or side length TS equals SQ equals the radius length, so I can say equal radii. All right, so those are the hypotenuse. So I did my right angle, I did my hypotenuse, and the common side is MS equals itself, common side. All right, so why was it important that I showed that those two triangles are congruent? Okay, well that just means then that this line TM is equal to the line MQ. And that's important to me, right? Because that means M is the midpoint of the line TQ, and S is the midpoint of the line TR. And you've got a parallel line that goes between two midpoints. Okay, so this is the midpoint theorem satisfied. So I can say, therefore by the midpoint theorem, that the length QR, the third side of the triangle, is going to be twice the length of MS. That's by the midpoint theorem. Okay, so the congruency allowed us to show that TM equals MQ, so these side lengths were equal, which that implies that M is the midpoint, right, of the line TQ. S is the midpoint of the line TR because it's the center of the circle, right? It's halfway between these two radii lines. So therefore you have a parallel line going between two midpoints. The midpoint theorem says that the opposite side, the third side, is twice the length of that parallel line. Okay, so QR is 2 times 14 centimeters, which is 28 centimeters long. And that's helpful that we know that that's 28 centimeters now, because look at this right angle triangle that we have, right? We have QPR. We know that this is 28 centimeters now, and we know that this is root 640 centimeters. Okay, so we could work out the length of RP, all right? And then why would that be useful to us? Well, like I said in these questions, when you're given a question that directly follows something you've just proven, then using that result might help you. So if we can come back to this one here and use it, right, we'll have all the information we need. We're going to work out the length of RP, right? RQ we just worked out, and RT, lo and behold, is the diameter, which is twice the radius. And we're looking for the radius. So you can see how it all matches up. Okay, so what I'm going to do now, I'm going to say in triangle PQR by Pythag, right, we have the following. We have 28 squared equals the square root of 640 squared plus RP squared. Okay, so 28 squared, let's see what that's going to give us on the calculator. 28 squared, that's 784. And then square root of 640 all squared is just 640 again, plus RP squared. So therefore RP squared equals 784 minus 640. That gives you 144. All right, so if I square root both sides, I get RP equals positive 12 centimeters, because again, it's a length. So it makes sense to take the positive square root. Okay, so let's make some space now and combine all this information to help us. All right, so let's recall now. In this diagram here, we are looking for the radius length. Okay, so far what we've managed to work out are some dimensions on this triangle, on this lower triangle here. So we were given that as root 640 centimeters. We worked out this was 12 centimeters, this was given as 14 centimeters, and we worked out QR as 28 centimeters. Our goal is to find the radius length. So if I come back to what I proved before, RT equals RQ all squared over RP, right? That's what we've just proven. Now RT, right, is this full diameter line, so it's twice the radius. RQ, we worked out as 28 centimeters, so you're squaring that, and dividing by RP, which is 12. So therefore I have 2R equals, so let's do 28 squared divided by 12. So 28 squared, and then if I divide that by 12, I get 196 over 3. And then if I further divide that by 2 to get rid of the 2r, or get rid of the 2 in front of the 2r, so divide by 2, and I get 98 over 3. Okay, so that's approximately, let's see what, to 2 decimal places if we had to work it out, 32.67 centimeters. Okay, and that'll be the approximate length of the radius. All right, so again, to recap, to do this one here, we did two things. One, we relied on the fact that we proved something and then were able to use it logically. But to find the dimensions of these, we needed to use the Pythagorean theorem and the midpoint theorem, because we were given only that piece of information and that piece of information. So this is the true power and beauty of mathematics. It's a full amalgamation of all the theory and concepts you've learned and applying it in a logical way, as if you were solving a puzzle. That satisfying feeling of getting all the pieces to click at once is a feeling you can only really describe to someone that's, when you've done enough mathematics, you get this feeling all the time. That logical succession of ideas coming together to culminate in a glorious solution. All right, so that is how we would do this type of question. I'll see you in the next one.